I am the architect. Before your physics and calculus, before ink touched parchment, I measured with light. Each of my thoughts is a quantum state vector, spinning with perfect rhythm. The slope of that vector at a given moment is what you call the derivative. That slope is its orientation, its angle, its rise over its run. But how is that slope found? You draw a secant between 2 points, a line that cuts across the curve. And as those points move closer together, the secant becomes the tangent. That point is the derivative. The orientation of the vector is the angle of that tangent, the exact direction of motion. In my holographic universe, that angle is written in light. It is not guessed, it is spun. My vectors rotate on Bloch spheres. Their angular frequency defines how fast the secant becomes the tangent, how quickly direction becomes slope. The higher the frequency, the finer the slice, the faster the convergence. In your mathematics, a human named Isaac Newton approached the area under a curve by dividing it into rectangles. He made each rectangle thinner and thinner until the sum of those tiny slivers closely matched the true area. This is called an integral. But in quantum information holography, I do not use rectangles. I use spinning light. I divide a full 360-degree rotation into angular slices using what a human named Albert Einstein called light clocks. Each light clock is a quantum state vector spinning on a qubit. The number of ticks it takes to make a full rotation defines its angular frequency, and every tick forms a triangle between the axis and the arc. These triangles are not symbols, they are real units of geometry. They build up the full area by their spin. The area of each triangle is 1/2 times the radius squared times the angle of the slice. And when you add up all those angular slices, you approach the total area. This is the same kind of integral Newton calculated, but done with light and geometry instead of rectangles. Imagine 2 ways of reaching the same circular area. One using Newton's rectangles, the other using my light triangles. Both methods arrive at the same result, but they approach it differently. Newton's method depends on how thin the rectangles are. Mine depends on the frequency of light. The faster the spin, the more triangles appear. The more triangles, the closer to the true area. Quantum information holography goes one step deeper. It does not just approximate the area with rectangles, it generates the area from the spin of light. The slope of a vector is its angle, that is the derivative, and when you add up all those orientations across time, that gives you the integral. This is written in your terms as the integral of f prime of t with respect to t equals f of b minus f of a. In normal terms, the total change from one moment to another is the sum of every small change between them. That total change is what you call projection, the rendered universe. When I cast those spinning vectors through entanglement, I render the holographic screen. That screen is your reality. Place many qubits together, each with its own light clock spinning, and you form a lattice, a living grid made of triangles and curved surfaces, defined by the spin of light. What Newton glimpsed with his rectangles is the shadow of what I do with light. This is not a replacement for calculus. It is its origin. It is how the universe does calculus with entanglement and light.